Hello, chemistry students. Welcome again to our General Chemistry 2 class. So for this video, we are going to tackle colligative properties of solution. For the objectives, number 1, describe the effect of concentration on the colligative properties of solutions. 2, calculate the boiling point, elevation, and freezing point depression from the concentration of a solute in a solution. And 3, calculate the molar mass from the colligative property data. Let's have first unlocking of difficulties. Beginning with vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. Boiling point is the temperature at which vapor pressure equals the external atmospheric pressure. Dilute solutions are solutions whose concentrations are equal to or less than 0.2 molar. Non-volatile substances are those with no measurable vapor. Osmosis is the net movement of solvent molecules through a semi-permeable membrane from a pure solvent or a dilute solution to a more concentrated solution. Osmotic pressure is the pressure required to stop osmosis, and semi-permeable membrane is a membrane that separates two compartments that allows solvent molecules to pass through but blocks the passage of solute molecules. In the previous videos, we described a concentrated solution as the one of higher solute concentration. So in this picture, you will see in the left picture, the T that is more concentrated than the other one. So the darker color of the solution indicates that it has a higher concentration than the in this molecular representation of dilute and concentrated solutions, you will see greater number of solute particles in the concentrated solution greater than the number of solute particles in the dilute. Let's prepare a solution of 1 molar concentration. So in preparing a solution with 1 molar concentration, you first measure 1 mole of a solute. As we know, 1 molar means 1 mole of solute dissolved in 1 liter of solution. So you add 1 mole of the solute in the container, which can be filled with 1 liter solvent, or 1 liter, you can prepare 1 liter solution. Then you first add a small amount of the solvent, dissolve the amount of solute that you added, that's 1 mole of the solute, dissolve, and then fill in the container with to make a volume of 1 liter. So that's how you prepare 1 molar of solution wherein the solute is solid and the solvent is liquid in this case. Let's have the effect of temperature on solubility. What is the effect of temperature on solubility? Generally, when the solute is solid, an increase in temperature increases solubility of a solid in a liquid. That's also the reason why when you are preparing coffee, it is easier to dissolve sugar, coffee, or powdered milk in hot water. This process is endothermic because in order to dissolve solid, it needs to absorb heat in order to separate its components. And in separation of its components, energy is required to break the intermolecular forces. That's why this process is always endothermic. That means that the energy of the solution is greater than 0. On the other hand, an increase in temperature decreases solubility of a gas in a liquid. So, increase in temperature results to lower solubility of gas in a liquid. So, this is true when the solute is gas and the solvent is liquid. And this process is exothermic. So if between solid and liquid in endothermic process, the energy of the solution is greater than 1, between gas-liquid solution, wherein gas is the solvent, the increase in temperature, which is resulting to decrease in solubility of gas in liquid, the process is exothermic, meaning energy is released by the system and the energy of the process is less than zero or negative. What about the effect of pressure on solubility? This is more remarkable. The effect of pressure on solubility is more remarkable when the solute is gas and the solvent is liquid, or in a liquid solution wherein the solute is gas. So notice in this illustration, we have in the first figure or diagram, we have a separation of gas particles and liquid particles. As you increase pressure, more gas molecules or particles are in contact or closer or distributed with liquid phase. So meaning greater attraction or greater connections between the gas and liquid phase. Or in short, there is greater solubility of gas in the liquid when pressure is added. So generally, an increase in pressure increases solubility of a gas in a liquid. When you shake, for example, a carbonated drink where there is pressurized carbon dioxide, you will notice when you open the bottle, you will hear a popping sound. Same with wines or alcohols. When you open the bottle, there is sudden release of carbon dioxide. So the pressure is being released when or decreased when you open the bottle of soft drink or a beverage, and therefore giving us the popping sound effect by the process. When a non-volatile solute is added to a solvent, three physical properties of the solvent in particular change. These properties are known as boiling point elevation, freezing point depression, and vapor pressure. These are also known as colligative properties. What are colligative properties? Colligative properties are properties that depend on the number of the solute particles in a solution and not on the nature of the solute particles. They are collectively called colligative properties because they are bound with the same or from the same origin, which is the number of solute particles, not the nature of the solute particles. We have four colligative properties of solution, but these are specific to non-electrolytes. Again, non-electrolytes, as defined earlier, are those whose concentration are or is lower than, equal to, or lower than 0.2 molar. These four colligative properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Let's have first vapor pressure lowering. To define again, vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. In this illustration, you will see in the left side pure solvent. When you add solute, as in the right side, represented by the green spheres, the concentration of solvent particles is decreased. That is to maintain the equilibrium between the solute particles and the solvent particles. What is the effect of addition of solute particles? This is explained by Raoult's law. Raoult's law states that the pressure of a volume of a solvent over a solution is given by the vapor pressure of the pure solvent times the mole fraction of the solvent in a solution. In equation, that is P sub 1 equals the product of X sub 1 and P sub 1 superscript O. P sub 1 means vapor pressure of a solvent over a solution. So this is the vapor pressure of the solvent when it has a solute particles. X sub 1 is the mole fraction of the solvent. P sub 1 superscript O is the vapor pressure of the pure solvent. So for example, the solvent here is water. So what is the vapor pressure of that pure solvent, which is water? So what we are looking for here is the vapor pressure of the solvent when there are solutes dissolved in it. So that is P sub 1. Vapor pressure lowering is a true colligative property that is independent on the nature of solute but directly proportional to its concentration. So I have emphasized colligative properties are independent of the nature of solute. Regardless of the nature of solute, the colligative properties are bound by the same origin, which is the number of solute, not by the nature of solute. So this colligative property is directly proportional to its concentration. So the vapor pressure lowering is proportional to concentration, meaning you increase the concentration, you increase the number of solute, you continue to lower the vapor pressure. So increasing concentration means lowering of vapor pressure. So change in vapor pressure or vapor pressure lowering is directly proportional to concentration. So vapor pressure lowering may be determined or calculated mathematically using the equation mole fraction of solute. So earlier we had X sub 1. X sub 1 is mole fraction of solvent. X sub 2 this time means mole fraction of solute. The other, P sub 1 superscript O, is still the vapor pressure of the pure solvent. In expanded form, we have the vapor pressure of the pure solvent minus the vapor pressure of the solvent over a solution equals the product of mole fraction of solute and the vapor pressure of the pure solvent. Or vapor pressure lowering is equal to the difference between the vapor pressure of the pure solvent and the vapor pressure of the solution or solvent over a solution. We always assume that the vapor pressure of the pure solvent is greater than the vapor pressure of the solution or solvent over a solution. What is the reason for this? The disorder. As we have established, the solubility is favored by increase in disorder, or vice versa, increase in disorder favors solubility. So since there is greater disorder when solute is dissolved in a solvent, there is smaller tendency for the solvent particles to break away from the solution, and therefore causing a lower vapor pressure, because vapor pressure is a result of escape of particles from the liquid. So the smaller number of particles escaping from the liquid, the lower the vapor pressure, because the lower number of particles result to lower pressure exerted by the vapor or by the molecules. Again, delta P means or indicates a vapor pressure lowering. So that's how we denote vapor pressure lowering as a colligative property, delta P. P sub 1 superscript O, meaning vapor pressure of the pure solvent. P sub 1 of the solvent over solution. X sub 1 is mole fraction of the solvent. X sub 2 is the mole fraction of the solute. If you have several volatile components dissolved in certain solvent, then you use the Dalton's law of pressure. But first, you You compute for the individual pressure, vapor pressure exerted by the components, and then you use the Dalton's-gas law equation, which is the total pressure equals the sum of the partial pressures exerted by the individual gases in the mixture. Okay, let's have a sample problem. To read, a solution contains 82-gram glucose in 322-gram water. Calculate the vapor pressure of the solution at 25 degrees Celsius. What's the vapor pressure lowering? Given here, we have pure solvent, water. Its vapor pressure is constant at given at 23.75 millimeters mercury at 25 degrees Celsius. So we are looking for two. One is vapor pressure of the solution, or vapor pressure of the solvent over solution, and the vapor pressure lowering. Since there is a presence of a solute in a given solvent, that's 82-gram glucose dissolved in 322-gram solvent, we assume a lowering of vapor pressure, because that's how Raoult's law explains the effect of solute particles in vapor pressure of a solvent. So first, let us convert the given masses of solute and solvent to moles. So to convert 82 grams glucose is C sub 6, H sub 12, O sub 6. It has a molar mass of 180.2 grams. That molar mass is equal to 1 mole, to give us the conversion factor 1 mole glucose over 180.2 gram glucose. So we substitute the given mass of glucose 82 gram. We multiply by the conversion factor taken by the equivalent relationship between 1 mole of glucose and molar mass of glucose, which is 1 mole over 180.2 grams. We cancel gram and then divide 82 by 180.2. We have 0.455 mole. So 82 gram glucose is equivalent to 0.455 mole. For water, we are given 322 gram. So to convert that to mole, we use the molar mass 18.2 gram. That's equivalent to 1 mole. We cancel gram and then we divide 322 by 18.02. We get 17.9 moles. So 322 gram is equivalent to 17.9 mole of our solvent water. So first, let's compute for the vapor pressure of the solution. So that is vapor pressure of the solvent over a solution. So using the equation x sub 1, p sub 1, we first get the mole fraction. X means mole fraction of the solvent, as indicated here, water. So water is our solvent. So to do that, we will use the mole fraction equation that we discussed in the first video on solution. We have mole fraction of the solvent divided by the mole fraction of the solvent plus the mole fraction of the solute, or simply the mole fraction of the solution. The calculated mole fraction of the solvent is 17.9. Divide that by the total moles of both the solute and the solvent, which gives us 17.9 plus 0.455 equation. So dividing 17.9 by the sum of the solute and solvent, we will have, and then cancel mole, we will have 0.795. So 0.795 is now the mole fraction of our solvent. We can now compute for the vapor pressure of the solution using the equation P sub 1, or vapor pressure of the solution equals mole fraction of the solvent times the vapor pressure of the pure solvent. So substituting all the given and calculated, we have the mole fraction of the solvent as calculated, we have 0.975. Multiply that by the vapor pressure of the pure solvent, which is given here in the problem as 23.75 grams, millimeters of mercury. And then multiply the two, you will get 23.17 millimeters of mercury. This is now the vapor pressure of the solution or of the solvent over a solution. Is it greater than or less than the vapor pressure of the pure solvent? This is expectedly lower than the vapor pressure of the pure solvent because addition of solute again results to lowering of vapor pressure. Let's see. Let's calculate the mole fraction of the solute. So earlier we computed the mole fraction of the solvent, which is 0.795. 975. So this time we compute for the mole fraction of the solute, which is glucose. What is mole of glucose divided by moles of the solution? The answer is 0.455 is the number of moles of solute divided by the sum of the moles of solute and solvent. We will have 0.027478. So this is the mole fraction of the solute. Using now the equation for the vapor pressure lowering, we have the product of mole fraction of solute times the vapor pressure of the pure solvent. So substituting the calculated mole fraction of solute, we have 0.02478. Multiply that by the given vapor pressure of the pure solvent, 23.75 millimeters mercury. Getting the product, you will have 0.5885 millimeters of mercury. You can also use the other formula. Delta P means vapor pressure lowering. So you can also use the equation, the difference or vapor pressure of the pure solvent minus vapor pressure of the solution. So from the given, we have 23.75 millimeters of mercury minus the calculated vapor pressure of the solution. We have 23.17 millimeters of mercury without canceling the unit because you need to copy the same unit when doing addition and subtraction. Getting the difference between 23.75 and 23.17, the answer is 0.58, which is similar to the answer in the first computation in the left for the same vapor pressure lowering. So you can use either of the two equations to determine or measure, calculate for the vapor pressure lowering. But the answer should be the same. So the difference between the vapor pressure of the pure substance and the vapor pressure of the solution is 0.58 millimeters of mercury. So that's the decrease in the vapor pressure when you add 82 grams of glucose in pure solvent, which is water. Number 2, colligative property is the boiling point elevation. Boiling point, as we defined earlier, is the temperature at which the vapor pressure of a solution equals the atmospheric pressure, and that is indicated by the formation of bubbles. So boiling point elevation as a colligative property is defined as the difference between the boiling points of the solution and the solvent. So if earlier we had vapor pressure lowering as the difference between the vapor pressure of the pure substance and the vapor pressure of the solution, this time we have the equation delta T sub B means or is the symbol we denote is how we denote boiling point elevation. So delta T sub B as boiling point elevation is equal to the temperature or boiling point of the solution minus the boiling point of the pure solvent. So in here, we expect naman that the boiling point of the solution is higher than the boiling point of the pure solvent. You have to take note that when pure substance is added with a solute, let's say you dissolve a certain solute, the boiling point is always greater than the boiling point of the pure solvent. So as I had mentioned earlier, the small number of particles escaping to become vapor from a solution lowers vapor pressure. if there is lower vapor pressure when you add solute, it will also result to longer time it takes for the solution to boil, or greater amount of energy is necessary for the solution to boil. So if it is a pure substance and you are given the boiling point and then you add solute to that pure solvent, you expect the boiling point to be higher than the boiling point of the pure solvent. So for example, water's boiling point is 100 degrees Celsius. You add solute, you dissolve solute in water, you expect boiling point of the solution, resulting solution, to be greater than or higher than 100 degrees Celsius. Kailangan po munang ma-reach niya yung boiling point ng pure solvent, which is water, for example, 100 degrees Celsius. At 100 degrees Celsius, dahil may nakadissolve na solute, hindi agad siya magboboil. The temperature will continue to increase until such time that the vapor pressure has reached the same atmospheric pressure. Saka lang po mag-start ng boiling. So addition of solute always results to increase in boiling point. This is due again to the addition of solute particles, which inhibits the faster vaporization of the solvent particles, thus taking longer time to reach the same atmospheric pressure by the vapor pressure. Boiling point elevation is directly proportional to the molality, concentration of a solution in molality. And because we have a constant of proportionality, introducing that, we have boiling point elevation equal to a constant. Boiling point constant, what we mean by K sub B is the boiling point constant times the molality of the. We have here in this phase diagram vapor pressure and temperature. So notice the a difference in the vapor pressure curve of pure water and solution. So notice at 100 degrees Celsius and 760 millimeters mercury, water will start boiling. But if water is added with solute to become a solution, the solution will require higher amount of energy, or it will reach a higher temperature before it will start to boil. Again, if it's a pure solvent water, for example, atmospheric pressure is 180 m or 760 millimeters mercury. Vapor pressure of a liquid of water is particularly reaches that same atmospheric pressure at 100 degrees Celsius. But if it has a solute dissolved in it, and it is a solution, then the boiling point must be higher than 100 degrees Celsius, as I had emphasized earlier. You add solute to the pure solvent water, you also increase the boiling point. Okay, so a solution will have a lower vapor pressure because of addition of solute particles and consequently higher boiling point. It will take longer to boil a solution. It will also require higher energy and therefore higher temperature for its boiling point. The third property is the freezing point depression. This is defined as a positive quantity which gives the difference between the freezing points of the pure solvent and the solution. So if earlier we expect boiling point of solution to be greater or higher than the boiling point of the pure solvent, this time freezing point of the solution is always lower than the freezing point of the original or of the pure solvent. So in equation, we have freezing point depression equals freezing point of the pure solvent minus the freezing point of the solution, or the solvent over a solution. freezing point depression is also directly proportional to the concentration. So introducing the constant of proportionality, we have freezing point depression as equal to freezing point constant times mula. We have here freezing point depression and boiling point elevation constants for selected solvent. Let's have water. The freezing point of pure solvent water is 0 degrees Celsius. The freezing point depression constant, or K sub F, is 1.86. The boiling point of water is 100 degrees Celsius. Its boiling point elevation constant, or K sub B, is 0.512. So K sub F and K sub B, or boiling point depression constant and boiling point elevation constant, will be needed in doing calculations involving freezing point depression and boiling point elevation. Let's have this simple problem. An antifreeze solution is prepared containing 50 cubic centimeter of ethylene glycol with a chemical formula C sub 2, H sub 6, O sub 2 with a density of 1.12 gram per cubic centimeter in a 50 gram of water. Calculate the freezing point of this 50-50 mixture. The given freezing point depression of water, pure solvent water, is 1.86 degrees Celsius per molal, which is also indicated in the table in the previous slide. So first, let's determine the mole of ethylene glycol. So to get this, we need to consider the given volume of the solute, which is 50 cubic centimeters, and its density, which is 1.12 gram per cubic centimeter. We know that the formula of density is mass over volume. So if we are given volume, then we derive mass as density is mass over volume. So we derive mass as density times volume. So that will be volume 50 times the density 1.12 gram per cubic centimeter. Cancel cubic centimeter, we will get gram. And then to convert gram to mole, we use the molar mass of glycol, which is 62.04. 1 mole in the numerator in order to cancel denominator, because we need to cancel denominator of the ethylene glycol, our solute, and the unit of the molar mass of our solute. So we will have mole as the unit left. So that will be our mole of the solute. Next is to calculate for the molality of the solution. The given mole, or the calculated mole of the solute is in step 1, 0.903 mole. Divide that by the mass of the solvent. It has to be expressed in kilogram because molality is mole of solute over kilogram of solvent. The given mass of the solvent is 50 gram. You convert that to kilogram, so that will give you 0.0500 kilogram. 0.903 mole divided by 0.500 kilogram will give us 18.1 mole per kilogram, or molal. Step 3 is to compute now for the freezing point depression. The freezing point depression is determined by the formula freezing point depression constant times molality. The given K sub F for pure water is 1.86. We substitute that here in the equation. Degrees Celsius per molal multiplied by the calculated molality or concentration of the solution in step 2, 18.1 molal. We cancel the unit molal. We now have temperature left as the unit. 1.86 times 18.1 will give us 33.7 degrees Celsius. Calculating now the freezing point of the mixture, we derive the formula for the freezing point of the solution from the freezing point elevation formula, delta T sub F equals freezing point of the pure solvent minus the freezing point of the solution. So deriving the freezing point of the solution, or T sub F, we have freezing point of the pure solvent minus the freezing point depression. So the freezing point of the pure solvent is given as 0 degrees Celsius, as indicated in the table in the previous slide. That's 0 degrees Celsius, the freezing point of water, minus the calculated freezing point depression in step 3, we have 33.7 degrees Celsius. So the answer is negative 33.7 degrees Celsius. This is now the freezing point of our mixture. So again, the pure solvent we have here is water. Its freezing point is 0. After adding ethylene glycol amounting to 50 cubic centimeter, notice the freezing point went down. So it decreased. So always remember that addition of solute in a solvent results to a decrease in the freezing point, or the freezing point of the pure solvent is always greater than the freezing point of the solution, or of a solvent with added solute. The fourth colligative property is the osmotic pressure. This is defined as the pressure required to stop osmosis. Osmosis is the process wherein solvent particles are passing through a semi-permeable membrane from a region of lower solute concentration to higher solute concentration. Or if we are considering concentration of solvent, movement of solvent particles from a higher solvent concentration to a less or smaller solvent concentration. Osmotic pressure is calculated as number of moles times the gas constant times temperature divided by all over the volume, or simply molarity times the gas constant and temperature. We know that the gas constant is given as constant as 0.0821 mole/Kelvin over atm that liter. So in this illustration, we have two systems. One is containing, the first beaker contains pure water and a semi-permeable membrane with a solution that is concentrated. In the other, we have dilute. So the more concentrated solution, which is the one in the smaller bag, means higher solute concentration. So between water and the concentrated solution, there is higher solvent concentration in pure water. So the semi-permeable membrane where the concentrated solution is contained will allow the passage of the pure solvent particles to the concentrated solution. So solvent particles from the pure water will pass through the concentrated solution inside the bag. So the passage is allowed by the semi-permeable membrane. So this will result to getting for the container, smaller container, to become bigger, because water particles, solvent particles, will pass through the solution through the semi-permeable membrane. So that's osmosis, and osmotic pressure is required in order to stop osmosis. The osmotic pressure, why do we need to stop osmosis. This is especially in relation to the human body or the living things. We have to control the entry and exit of materials from inside to outside or vice versa in the cell. So the passage of materials inside and outside of the cell must be controlled. So that's why we measure and control osmosis by determining osmotic pressure. Let's have this problem. Calculate the osmotic pressure of a 15 °C of a solution. Calculate the osmotic pressure of a 15-degree solution prepared by dissolving 50 grams sugar with the chemical formula C sub 12 H sub 22 O sub 11 in enough water to form 1 liter of a solution. So first we determine the mole of solute. We have the given mass of solute, 50 gram sugar with this chemical formula. So as we always do, converting mass to mole is considering the molar mass of the substance. The molar mass of our sugar is given here at 342.3 gram. So to convert 50 gram of our sugar to mole of sugar, we do the operation 50 times 1 divided by 342.3. That will give us, cancelling gram, that will give us 0.146 mole. Next is to compute for the concentration in molarity. In terms of molarity, molarity is determined by dividing mole of solute by the volume in liter of a solution. The calculated mole of solute in number 1 is 0.146 mole. The given volume of the solution in the problem is 1 liter. So dividing 0.146 mole by 1, that will give us 0.146 molal. We are now ready to compute for the osmotic pressure. Osmotic pressure is given as the product of molarity, the gas constant, and temperature. 0.146 mole per liter is the concentrated calculated in number 1 of our solution. That's 0.146 molar or mole per liter. We have to express molar in another form in order to do cancellation. Multiplying that by R. R is the gas constant, which is given at 0.0821 atm dot liter over mole dot Kelvin, times again by the temperature. The temperature is given at degrees Celsius. We cannot substitute degrees Celsius in an equation. We have to convert that to Kelvin. And in doing so, we add constant 273 to 15 to give us 278 Kelvin. We do similar units between numerator and denominator. So we have mole, liter, and Kelvin. We have atm left as the unit, the final unit. Doing the operation 0.146 times 0.0821 times ulit 278, that will give us a total of 3.45 atm. That now is the osmotic pressure of a solution. A laboratory experiment on colligative properties directs students to determine the molar mass of an unknown solid. Each student receives 1 gram of solute, 225 ml of solvent, and information that may be pertinent to the unknown. So there are 2 students. Student A determines the freezing point of her solution to be 6.18. She is told then that her solvent is cyclohexane, which has a density of 0.779 gram per ml. Freezing point is 6.50 and freezing point depression constant is 20.2 degrees Celsius per molal. So for student A, she will have to do the following steps in determining or in getting to come up with her requirement. So first is to determine the freezing point depression. So that may be determined by the formula of freezing point depression as the difference or freezing point of the pure substance minus the freezing point of the solution. The freezing point of the pure substance is given at 6.50 degrees Celsius. Minus 6.18 degrees Celsius is the freezing point of the solution. Getting the difference, the freezing point depression is 0.32 degrees Celsius. Number 2 is to calculate the molality of the solution. Using the formula, the freezing point depression equals the product of freezing point depression constant and molality. We have molality derived as freezing point depression divided by the freezing point depression constant. Substituting the values, we have the freezing point depression calculated in step 1, 0.32 degrees Celsius, divided by the given freezing point depression 20.2 degrees Celsius per molal. You cancel degrees Celsius, you now have 0.016 molal. Number 3 is to compute for mass of solvent. Mass of solvent may be determined using the step volume to mass to moles. The given volume of the solution, of the solvent rather, because you are looking for the mass of solvent. The given mass of solvent in the problem is 225 milliliter. Multiply that by, because you derive the formula from the formula of density. Density equals mass over volume. You derive mass as volume times density. So volume 225 times density, the given density is 0.779 gram per milliliter. You cancel milliliter, multiply again by the conversion factor in order to convert gram to kilogram. This is only to convert gram to kilogram after getting the mass from the volume and density of the solvent. So that will give you 0.175 kilogram. Then, after getting the mass of solvent, we are now ready to get the moles of solute. The moles of solute may be determined by using the equation of molality. Molality is mole of solute over kilogram of solvent. We derive mole of solvent as molality times mass of solvent. The given molality as computed in step 2 is 0.016 molal times the mass of solvent calculated in step 3, 0.175 kilogram. So cancelling kilogram between the two, hindi lang po na-indicate dito, but the units for molality is mole per kilogram. For the mass, we have kilogram. You cancel numerator denominator kilogram, you will be left with mole as the unit here. 2.8 times 10 raised to negative 3 mole or 0.0028. And finally, for the computation of molar mass, you just use the formula mass of solute over moles of the solute. So we have 1 gram of solute, divide that by the calculated mole of solute, 2.8 times 10 raised to negative 3 mole. That will give you 3.6 times 10 raised to 2 gram per mole, or 360 gram per mole is the molar mass of our substance or unknown solid. Student B determines the osmotic pressure of his solution to be 0.846 atm at 25 degrees Celsius. He is then told that his solvent is water with density of 1 gram per milliliter, and the density of the solution is also 1 gram per milliliter. So the following steps are to be undertaken by student B. And in doing so, beginning with the computation of molality, we derive molality from the osmotic pressure equation MRT. So we derive molarity as osmotic pressure over or divided by the gas constant times temperature. Substituting the given values, we have the given osmotic pressure, as B is given the osmotic pressure 0.846 atm, divided by the gas constant, again 0.0821 liter that atm per or over mole that Kelvin, times the temperature in Kelvin 298. Cancel the similar units between numerator and denominator, atm and Kelvin. You will be left with mole per liter unit. So we shall have 0.0346 mole per liter for the molality of the solution. We now compute for the volume of the solution. For the volume of the solution, you simply add first the mass of solute and the mass of the solvent. The mass of solute is 1 and the mass of the solvent is 225 times 1 because of the density 1 times 1 gram per ml. That will give you the same mass, 225 gram. Multiply that or add that by the mass of solute 1 gram. You will have 226 gram as the mass of the solution. So for the volume of the solution, you derive from the formula density equals mass over volume. So volume is the ratio of mass to density. So the mass of the solution is 226 divided by the volume of the density of the solution is also 1 gram per ml. Canceling gram, you will have 226 milliliter. So that will be equivalent to 0.226 liter. For number 3, compute for the mole of solute. The mole of solute is can be taken from the a formula of molarity, which is mole of solute over liter of solution. We derive mole of solute as the product of molarity times volume, or volume, mass molarity times volume. The calculated molality in step 1 is 0.0346 mole per liter. The calculated volume of the solution in step 2 is 0.226 liter. We cancel similar unit between numerator and denominator liter. We will be left with mole. So number 3 will give us 0.00781 mole, which is the mole of our solute. And lastly, the molar mass of the solution, of the substance, of the unknown substance. So earlier, student A was able to determine her unknown or his unknown. So this time, student B is determining his unknown. So for the molar mass, we use the formula mass of solute over mole of the solvent. Of the solute, same substance. So 1 gram is the mass of solute divided by the moles of solvent as solute as calculated in step 3, 0.00781. So 1 gram divided by 0.00781 will give us 128 gram per mole. So this is now the molar mass of the unknown solid of student B. So for more practice, you can do the following problems. That will be all for this topic. Thank you for watching. Until next time.